remembers what ionization energy is from honors chem? Anybody? I heard some folks talking about it. Anyone have any thoughts from back in periodic trends days? Hi. Yeah.
Is it like how much energy it takes for like an atom to lose like gain or lose an electron, or lose an electron?
Lose an electron. Yep. So different atoms, different elements are going to either gain or lose electrons to become ions. But when we talk about ionization energy, that definition is based on losing one electron. Okay. And so we are going to talk about that when we review periodic trends, which will be the next unit. We'll talk about that again in terms of the trends going across the periodic table down groups. Okay. But we are also going to talk about it in the context of the emission spectra and the electron jumps that we talked about in the last section. So we're going to talk about that here, talk about a little bit of evidence probably tomorrow for more evidence for the sub-levels that we see, that we know for the electron configurations now, but we've got some other evidence relating to ionization energy. And then plan is lab on Friday. Okay, so that is the plan for the rest of the week. So the beginning of this is going to be a little bit complicated to explain. I'm not going to explain the theory fully, and I'm going to give you a link to a textbook chapter where I got some of the images from. You're not responsible for the information on the first couple of slides. It's just trying to give you context for what's going on. So it's not in your study guide, but the slides will be posted, and you'll have access to the web page, okay? Well, this is in your study guide. Also, just to note, you've got a weird page in the beginning of your study guide packet because I think either he messed up when he put this together or he made a different choice than I would have made about what to include. So I took out a page and stapled a page from the old curriculum in there because it has this diagram, which is what we need sort of the context for what we'll be talking about. So we've talked about this idea of our emission spectra and how electrons transitioning from one level to another level gives off a photon of light, basically dumping that energy as it falls back down to a lower energy level. And we talked about how we can see some of those transitions, the ones that go, for the hydrogen atom at least, from any level to the second energy level. And then the smaller transitions to energy level 3, we can't see because they're too small energy, longer wavelength, they're going to be infrared. The bigger jumps going down to the ground state, n equals 1, are too big. They're going to have shorter wavelengths that we can't see. They'll be in the UV. But if we were to have a detector that could look at all of these things, this is kind of what it would look like, what the whole series would look like if we had a spectrum going from 0 to 1800 nanometers in wavelength. Okay. We've been talking about it in terms of wavelength, but the wavelength of the wave, so here's our wave, and peak to peak or something similar, that's our wavelength, but we can also think about the wave in terms of its frequency, right? How many waves are happening in a particular amount of space or time, depending on how you're talking about it. Okay, so frequency is going to be inversely related to wavelength. The longer the wavelength, the fewer waves we have in any given space, right? So we can show this same kind of diagram, but in terms of frequency, and that is because we'll be actually using frequency to do some calculations with this. So the whole point of this is just to point out that wavelength and frequency, we'll talk about these letters, are inversely related. But when we plot these out on a frequency chart instead of a wavelength chart, it's the same thing, it's just flipped around, right? So what you can see is our infrared series here, our visible series shown with the colors that we can see in the spectroscope, and the ultraviolet series over here. And what you'll notice about each one is that there's a convergence where the lines get closer and closer together, meaning that the energy levels are getting closer and closer in energy to the one previously. So we start out with a big gap, and then a smaller gap, and then a smaller, until they basically run together at the end, okay? And we can actually sort of also look at this in the context of the energy levels on a vertical diagram too. This is, again, just to sort of show you that what we've been talking about here is the same thing that we're seeing on this spectrum, okay? So these jumps down to the second energy level show up over here. Jumps down to the first energy level are going to be over here on the higher frequency side, okay? So what happens when we get to the point where they're all running together? And if you have noticed in the energy diagram, you see this level infinity at the top, right? It doesn't just go 1 through 7 and then stop. There's a level infinity, okay? Level infinity is what happens when we get so converged that that any difference in energy is not going to put us into a higher energy level. It's just going to pop the electron right off the atom, okay? So if we get past this convergence limit, we're going to ionize. We're going to lose that electron rather than having it jump up to a higher energy level, okay? So that's the ionization that we're talking about here when we talk about ionization energy, okay? So understanding that there is this convergence and that the infinity level is essentially ionization, that's the important thing to take home from this. And if you want to read through the whole textbook chapter that explains all of this and goes into more detail, I will post it on Canvas, okay? But this is not stuff that you're responsible for. Any questions on this? Okay. Okay, so if we look at the text that's above that vertical energy diagram in your packet on the second or third page, the page numbers get a little weird because I had to insert that page. This kind of gives you everything that I just said in text, okay? So highest possible energy level is the frequency at which we get this convergence, okay? If we can figure out what that frequency is, the frequency of the wave that reaches that convergence point, then we can also calculate what the ionization energy is. And that's what we're going to do. So basically, if we have enough energy, the electron's going to go from a ground state to the infinite state, at which point the electron has been removed from the attraction of the nucleus and is forming an ion, okay? You'll notice that you have this equation here where we have, in terms of, we can think of it in terms of a single atom. We can also think of it in terms of a mole of atoms, which we will eventually be talking about. So if we have a hydrogen atom becoming an H plus atom, losing an electron, notice that it's in the gas state. So all of the calculations we're doing for ionization energy and the numbers that you get like on ptable.com for ionization energy, those are in the gas state. So just always be aware if you're asked about, like for a definition of ionization energy, make sure you're including that it's in the gas state, okay? So we can talk about it, again, for a single atom, we can talk about it in terms of large quantities of atoms, like a mole of atoms, okay? So that's essentially what the ionization energy is. It's the difference in energy from the ground state to that infinity state where the electron just leaves. Questions on this? Okay, so we're going to figure out how to calculate this. In order to do that, and I'm sorry, I don't know why, I meant to fix this slide earlier because I think I took it from the wrong PDF. I'm just going to change all these news to Fs. So this is a relatively new thing that they did. Frequency, the sort of symbol that we use for it in equations can be this, which is nu, which is Greek lowercase n. But we can also use F. Either one of these, you'll see them you'll see both of them depending on what textbook you're looking at. IB used to use the nu, but they changed to the F. So if you see the lowercase f in the context of these equations, it stands for frequency. Okay, but if you see the nu somewhere, don't think, oh my God, I've never seen that before. It's just another symbol that people use for frequency. So you've got in your data booklet, you have, remember that section 1 is your equations, section 2 is physical constants, okay? And you're going to be using both of these for this, to answer this kind of problem. And remember, you'll have your data booklet for all sections of the exam, so you will always have access to these equations. But the two that we're working on right now are the two at the top of section 1. If you don't have it right now, that's okay. You don't have to pull it out because it's here for you in your packet. One of them is the equation for energy in terms of wavelength, or in terms of frequency of a wave. So we're talking about energy in terms of electromagnetic waves. Okay, so there's obviously lots of different kinds of energy. In this case, when we're talking about the energy of light or other, whether it's visible or other parts of the spectrum, we have this equation that tells us that the energy of that photon, of that wave, is equal to Planck's constant times the frequency. And you might say, oh no, but I don't know Planck's constant unless you're a big Stranger Things fan, in which case you might want to sing the Never Ending Story song. If you don't know what I'm talking about, you're missing out. But also in section 2, in physical constants, I'm glad somebody laughed, thank you, you can see that you have Planck's constant right here. Okay. So we can calculate energy if we know Planck's constant and we know the frequency of the wave that we're looking at, the photon that we're looking at. Notice that frequency is given in two possible units. One of them is seconds to the -1. So this is where IB starts using this parameter where rather than writing per second in a unit, they're going to write seconds to the -1 power, okay? So you'll see the same thing if we have, say, density. Let me just throw another page in here for a second. So we talk about density is equal to mass over volume, right? That's how I would typically write it. In IB, they would say it's equal to mass times volume to the -1, okay? And the reason is that when they, for whatever reason, and I don't know if this is a British thing or what, or just like the people who run who design the IB curriculum, who are mostly British, but they, if you're drawing a graph, the units they give, so they'll say like density, and where I would put the units in parentheses, they use a slash. So they would write v to the -1, okay? And so they've used the slash to separate the thing that they're measuring and the units. So they can't use the slash to indicate that something is being divided in the units themselves, because that would be too many slashes. At least that is my understanding of why they do this. But you're going to see this over and over again, these things to the -1 or to the -3rd, and that just means it's on the denominator. Okay, a negative exponent just means it's in the denominator. We'll practice this more when we get other units that are like this. But when you see seconds to the -1, that's what it means. It's whatever it is you're measuring per second. Okay, but another unit that we can use for this is hertz. That's what hertz is things per second. It doesn't matter what the thing is. Okay, it's whatever you're measuring per second. It's the frequency of the thing that you're measuring. So you can use seconds to the -1, or you can use hertz, either one. You will see them when they give you quantities, it'll be in seconds to the -1. So it might take a while to get used to that. It probably took me like a year. So don't worry if that's messing you up. I will refer to it every time it comes up again. So then we have also, what if we have the wavelength but we don't have the frequency? Well, we can convert those using the speed of light, okay, because we're really talking about the wavelength and frequency of a light wave, okay? So the speed of light is also a constant that is in your physical constants section. So you don't have to memorize either of those numbers. You just need to remember that they're available to you in the data booklet, okay? We use lowercase c for the speed of light. Just like E equals mc squared, that's a different equation. We're not going to use that equation in this class. But we are going to use c. C is equal to lambda, so this is lambda, which is lowercase l in Greek. We like to use Greek in science. Okay, so that little kind of half of a stick figure thing is lambda, and that's what we use for wavelengths. So we can say that the speed of light is equal to the wavelength times the frequency of that light wave. Okay, but the speed of light is a constant. So if we have the wavelength, we can calculate the frequency. If we have the frequency, we can calculate the wavelength. And you're going to see how this comes into ionization energy in a little bit. Okay. You'll notice that we've got some scientific notation here. You may or may not have become familiar with that in previous or concurrent courses. So I'll talk about that in a second. I'm just trying to think if there is something else I need to talk about with those. No, so those are the two equations that we're going to be using kind of together. So if we look at the exercises, for example, you might be given energy and be asked to solve for frequency. Well, this is where a lot of what we do is going to involve some basic algebra moves where you rearrange the equation and solve for whatever you don't have. Okay, so you've done this before, even if you don't remember doing it. Some of you are like, yeah, I know how to do that at whatever. But some of you, it's been a long time since Algebra 1, okay? So, if we'll review that really quick. So say I'm given energy, I want to know the frequency. So the equation I'm using is the first one, right? Because it's got energy and frequency in it, and it's got this constant that we already know. So if I'm looking at this equation, E equals HF, but I want to solve for F, how do I do that? If I want to instead say F is equal to something. Yeah, so I'm going to divide both sides by h. So I can do whatever I want in this equation to move things around as long as I do the same thing to both sides, whether it's adding and subtracting, multiplying or dividing. Okay, so f is going to be equal to e over h. Now, you could also just plug things into e equals hf and then move the numbers around instead of moving the variables around. Whatever makes the most sense to your brain, okay? So my frequency is going to be equal to the energy divided by Planck's constant. So that's going to be 2.24 times 10 to the negative 19th power divided by Planck's constant, which is 6.63 times 10 to the negative 34th power. When I have something that is times 10 to the negative 19th or times 10 to the negative 34th, what can we say about those numbers? Are they big, small, really big, really small? Which one? Really small, right? Negative exponent means it's a very, very small number. The big number means it's very, very, very small, okay? But how do we do this calculation with our calculators? So I am going to be, for the next couple minutes, talking about the classroom calculators. So make sure you have one of those if you don't have your own, like graphing calculator or something. If you have your own graphing calculator, it might be a little bit different. The steps might be a little different. The buttons you push might be a little different. But the idea is going to be the same. Okay. Anybody else need one? Everybody got one? Okay.